Now we will start the next topic is the electrostatic potential energy. Electrostatic potential energy. The same thing we had done in the gravitation also. The potential energy is a scalar quantity and it is defined as, I am writing the definition first, it is defined as the amount of work done in bringing the charge from infinite to point in the space without acceleration, or in the space slowly without acceleration. It is defined as the amount of the work done in constitute a system of charge particle in bringing them from infinite to point in the space without acceleration. Is it clear or not? For example, if this is the Q1, this is the Q2, this is the Q3, and this is the Q4. So these 4-point charges are placed. So its potential energy is nothing but we have to do some work, right, in bringing these charge from infinity without acceleration, right, to constitute the system of charge particle. What the amount of work done is required, right, that work done is stored in the form of the potential energy. Is it clear or not? For example, if you consider for the 2-point charge system, for 2-point charge system, 2-point charges, suppose this is the Q1 over here, right, this is the Q1. So, and the other charge Q2 is bringing from infinity to some point over here, right? So what you have to do, suppose this is the fixed, right, and therefore you have to bring, and it will apply the repulsive force on this charge. If suppose the charges come this at this point, the Q1, this will apply the electrostatic force. So you have to apply the external force or not, right? You have to apply external force. So you have to do some work against the electrostatic repulsion of this. So that work is stored till when Q2 is moved from infinity to this point P at separation R. So you have to do some work. So that work, external work done in bringing this charge Q2 from infinity to point P is defined as the potential energy, right? The potential energy U. Is it clear or not? The potential energy is nothing but it is U. So you have to calculate the external work. Although when we will calculate the work for the 2-point system, suppose this is the Q1 and Q2, it is fixed and we are bringing this charge. So what the work you have to do, I will calculate this as we have done in the gravitation also. The work done comes to be the Kq₁ q₂ upon R. So for the 2-point charge system placed at separation R, their potential energy is given by 1 upon 4 pi epsilon naught Q1 Q2 upon R, right? In this expression, the Q1 and Q2 are placed with sign, whether it is positive or negative. The Q1 and Q2 are placed with sign. Is it clear? The SI, it is a scalar quantity. SI unit is joule, right? And it is a scalar quantity. right? Potential energy is scalar quantity, right? Copy this. One more important point you can write over here: the potential energy always defined for the conservative force, right? The electrostatic force is the conservative force. Now you should remember this: electrostatic force is a conservative force, therefore its potential energy is defined in this way. For the friction force is not conservative force. Any resistive force which is not conservative force, definitely, right, the potential energy is not defined, right? This is the one thing. Now I am going to derive this relation. Suppose this is the capital Q is placed, it is fixed, right? And you have to bring the charge Q from the infinity slowly without acceleration. So you assume that it is at separation x at some time. This is the charge Q to the electrostatic repulsion, and you have because you have to bring without acceleration, so you have to apply the external force which is equal to the electrostatic force, and this is Kq upon x square. Is it clear or not? Now you tell. If you at this point the external force is this, you want to move by the displacement dx, suppose, so the elemental work you have to do the external work into dx. Is it clear or not? This is the elemental work. One more thing, the elemental work is f into dx, but the x is decreasing, so therefore minus dx will be over there. Is it clear? And the total work would be found with the help of the integration of the external f external minus dx. And listen one thing, this f external is equal to at this point kq upon x square into minus dx, right? And here the x is equal to infinity up to this point p at distance r, right? You have to bring this charge. So from 0 to r. Is it clear or not? So you have to find the external work. So minus kq x raised to the power minus 2, 0 to r into dx, right? Minus kq, the integration is x to the power minus 1 from 0 to r, right? So it is equal to, wait for 1 minute. Its integration is minus x raised to the power minus 1 upon minus 1. This minus minus will cancel out. So kqr 1 upon x from 0 to r. Sorry, the r values from infinity to the x value from infinity to r. Now you will put the upper limit kq 1 upon r minus 1 upon infinity. So the external work is nothing but I am writing this side in bringing from infinity to point P is nothing but kq upon r, and it is stored in the form of potential energy. So this is the formula for the potential energy. This is the formula and this is the derivation. In the same way we have done in the gravitation also, right? Copy this. So let's do some question. For example, suppose this is the triangle, right? This distance is r, equilateral triangle. This is q minus q plus 2q, right? You have to write its potential energy, right? So the potential energy is nothing but the potential energy is a scalar quantity. So u1, u2 and u3. Again, there are the three terms. You are going to write the potential energy very fast. In the same way we have done in the gravitation. With sign you have to put the charges, right? Kq1 k, right? Q1 q2 upon r, Q1 q2 upon r, Q1 q2 upon r, right? Kq square upon r minus 3k 2kq square upon r, 2kq square upon r. The answer is minus kq square upon r. So this is the potential energy, total potential energy of this system of charged particles, right? Copy this. So the one more question you can write, if this is the square and the charge is placed over q, this is q, this is minus q and this is 2q, and the side is A, you have to write the potential energy of the system. Again, how many terms will be there? 6 terms will be there. U1, U2, right, U3, U4. So these are the 4 configurations. Now between this U5 and between this the U6. Is it clear? So this is the potential energy you have to write. So U1 plus U2 plus U3, U4, U5 and U6. Right. So U1 is what? K minus Q upon A. Right. K Q into TQ upon A. Right. K Q into 2Q upon A. Right. K minus Q into Q upon A. So these are the 4 terms, and the 5. This is K Q into Q upon A root 2, because if this is A, this distance is what? Say A root 2. And in the same way, minus Q and Q, K minus Q 2Q upon A root 2. Right. So you may write the total potential energy is Kq square upon A. It is minus 1, it is plus 2, it is plus 2, it is minus 1, right, it is 1 upon root 2, minus 2 upon root 2. So it is cancel out. So Kq square upon A, this is Kq square upon A, 2 plus 2, and this is equal to minus 1 upon root 2. So this is Kq square upon A, 2 root 2 minus 1 upon root 2. So this is the total potential energy of the system, right? Copy this. So the question, the same type of the question we are going to discuss. This is the cube, right? And on the each corner of the cube, the charge Q is placed over there, right? Like this. This is the charge Q, and you have to find the potential energy if the side of the cube is assumed to be the L. Right, this is the cube of side L. You want to write the potential energy terms, right? Can you tell me how many number of potential energy term will be there? Right, the number of terms will be, right, n minus 1 1 into 2, where n is the number of charges. Is it clear or not? For example, if there were the 4 charges, right, how many charges was present? Say 4. 1 2 3 4. So how many potential energy terms will be there? N minus 1 into 2, 4 minus 1 into 2. So 4 into 3 is equal to 2. So 6 terms we have calculated this. If these are the total number of charges 8, so number of potential energy terms will be n minus 1 upon 2. So 4 into 7 is equal to 28. So the total 28 terms we are going to write over here, right? First copy this, then I will explain. So again the same thing. If you consider the terms Kq upon L, where the 2 charges are present at distance L. So how many terms are there? Say 1, 2, 3, 4, 5, 6, 7, 8. So these are the 8 terms. 9, the separation is L, 10, 11, 12. So there are 12 such terms which where the charge are placed on the corner, right? In the same way, if you consider the one face, this is the Q1 Q, the distance is L root 2. So the potential energy is Kq upon L root 2. How many such term will be there? On one face, this is the one term and this is the another term, Kq upon L root 2. So in one phase, the 2 terms are there, and for the cube, there are 6 faces. So 6 into 2, 12 such terms will be there. Is it clear or not, you tell? Right. So 12 and 12, 24, only the 4 terms are remaining. And how they will be calculated? If this, you consider the cube of the diagonal, for example, this and this. So if this is L root 2, this is L. So what is this perpendicular? What is this cube diagonal? This is L root 3. How does it come? L root 2 whole square plus L square. So it is the cube diagonal is nothing but 2L square plus L square is equal to L root 3. So the two charges Q and Q are placed at separation L root 3. How many such charges are there? There are the 4 cube diagonal, right? This is the 1, 2, 3 and 4. Is it clear? So 4. So how many terms we have written? 12 plus 12 plus 4 is equal to 28. Only the 28 terms we have to write. Kq square upon L I am taking common, plus 12 upon root 2 plus 4 upon root 3. So this is the total potential energy for this question, right? Copy this. The electrostatic potential energy, potential energy due to solid bodies, right? Or due to continuous charge distribution, due to continuous charge distribution. For example, first I am considering the ring, right? This is the ring. Suppose this is the ring, right? And the total charge is capital Q, is placed on the surface of the circumference of the ring. The ring is radius r, right? The radius r. Is it clear or not? So, and the another charge is over here. It is suppose the small q, which is placed at distance x, right? So can you find the electrostatic potential energy between the 2-point charges, right? We can find. How to find the electrostatic potential energy? If you consider the small dq, right? This is the dq, small dq. I'm considering is the q0. So although all the charge is not possible to write, but for the small dq and this q0, which is present at distance small r, and I can write the elemental potential energy Kq₁ q₂ divided by r. And what is r? R is nothing but root over r square plus x square, right? And to find the potential energy, you have to integrate. So Kq0 dq upon r, you have to integrate Kq0 upon r, fine, and integration of dq. Integration of dq mean the integration of dq will be equal to what? The capital Q, total charge on the circumference of the ring. So Kq0 capital Q upon r, right? And the value of the r is nothing but root over r square plus x square. And this is the potential energy for this uniform ring, the ring, and this the charge, right? If this charge is present on the center, right? If x is equal to 0, that is Q0 is present, on center, right? If Q0 is present on center, mean this is the Q0 and all the charge capital Q on the circumference capital Q. The distance is r, right? This, although this is the 3D view, right? You may consider, suppose this is the ring and this is the Q0 and the charge is placed on the surface like this. This is the capital Q, right? So what will you write the potential energy? This Q0 is assumed to be the at distance capital R every time, or here you can put the x is equal to 0. So the potential energy is Kq₁ q₂ upon r, right? So this is the potential energy of this system, of this point charge and the ring, uniformly charged ring, right? Copy this. For example, one more question we can do, right? Suppose this is the charge, uniformly charged rod. The length of this charged rod is assumed to be the L, and the linear charge density is lambda coulomb per meter. And 1 point charge capital Q0 is placed at distance x, at distance r, suppose, right? This is the distance a, suppose. You have to find the interaction energy, fine, right? Interaction energy between rod and charge Q0. Rod and charge Q0. Right? You have to find this interaction energy. How to find? Listen one thing. At distance x, we cannot write the total potential energy of the system directly, but what can we do? At distance x, if we assume the elemental charge of the width dx, the charge is dq. Suppose this charge is what? Say dq, and this charge is what? Say q0. So this is what? X plus a. You understand or not? So I can write at least the potential, elemental potential energy between dq and q0. So k, right, q1 k q1 q2 upon x plus a. Is it clear or not? So if you integrate this, definitely we will get the total potential energy k dq q0 upon x plus a. So the common quantity will be come out from the integration. So this is the Kq0 at dq upon x plus a. What is the dq? Elemental charge of width, say dx. If the linear charge density is lambda coulomb meter, what will you write the dq? Is equal to lambda into dx. Is it clear? Lambda coulomb per meter mean in 1 meter the charge is lambda coulomb. Therefore in dx meter the charge is what? Lambda into dx. So therefore the dq is equal to lambda into dx. So here I will write k q0 lambda into dx upon x plus a. So this is equal to k q0 lambda, right, 1 upon x plus a into dx. And the value of the x varies from the element start from here, this side, and this side. So from x is equal to 0 to x is equal to capital L, right, we have to integrate from 0 to capital L. So this is kq0 lambda, and the integration of 1 upon x, you will remember 1 upon x integration is ln x, right, and 1 upon ax plus b integration, you must remember ln ax plus b. In multiplication of x is a, so it comes in division, right, but here the x into multiply by 1, so only the ln x plus a is the integration, and the limit varies from 0 to L, right. This side I can integrate to get the total potential energy k q0 lambda, right. Put the upper limit first, ln L plus a minus ln 0 plus a, right. So this is k q0 lambda, right, ln L plus a upon a. So 1 upon 4 pi epsilon naught, right, q0 lambda is equal to ln 1 plus, right, L upon a is the total potential energy of the system. So the question may be asked in different way, right. The rod may be placed in this way, and this is the q0. So then you know the integration in the previous chapter, right, we have done this type of the question. You will assume the elemental charge of dx with the dq, right. You will write the elemental potential energy and then you have to integrate, right. In this way you can write, you can do the potential energy of the different type of the system, right, if the charge is continuous distributed over the some body, right. Copy this. So now I am writing the self energy as we did in the gravitation, right. Self energy mean first for uniformly charged shell, right, of radius r, right, like this. So this is the shell, and if you give the charge, so listen one thing, the total charge assumed to be capital Q and the radius is r, right. So to make this system of the uniformly charged shell, you have to bring this charge from infinity to this point in the space, then you have to do the work, right. That work can be found with the help of the potential, right. We can do the formula, we can do the derivation later, but here you have to remember only The self energy of this shell is kq square upon 2r. Right. In the gravitational field, it was minus gm square upon 2r. Is it clear or not? In the same way, this for the solid, right? For uniformly charged, right? Solid sphere of radius r. Suppose this is the solid sphere, fine, and this is the charge distributed over the volume, right? Like this. This is the center, this is the radius r. The total charge is distributed over the volume. For this case, the self energy, right? You will write 3 upon 5 kq square upon r. This formula you have to remember, although we will do the derivation also, but directly you can use this formula for solving the question, right? Copy this. For example, if suppose we have the two shells, right? The charge on the one shell is assumed to be the q1, right? The radius is r1 and the charge is q1, and another shell of the radius r2 having the charge q2, right? Like this, and the separated by the distance r, their center. So you have to write down the total energy of this system of the two sphere. So the total energy is nothing but the interaction energy plus the self energy. So the its self energy is nothing but kq square upon 2r1, fine, plus this is the kq1 plus kq2 square upon 2r2 plus the self interaction energy kq1 q2 upon r. In this way you can write the total energy of this system, right? The another example I am giving, this is the shell, right? Shells, this is the shell, this is also the shell, right? For example, one shell is placed and the another placed is placed like this. Concentric two shells are placed having the charge, right? The having the charge q1 and having the charge, right, q2. Is it clear or not? So you have to find the self energy, total energy of the interaction, right? The total energy of the interaction is nothing but the self energy of this system, kq1 square upon 2r1, self energy of this system, kq2 square upon 2r2, plus the interaction energy between the two shells. So for finding the interaction energy between the two shells, this q1 charge can be assumed to be the center, right? And this is kq1 and the q2 charge is placed at distance capital R2. So this is the total energy of this two shells, concentric cells. Is it clear or not? One more thing, one more example you can assume. Suppose if this is the shell and this is the charge q, this is the capital Q charge placed on the surface. So what is the total energy of this system? The radius is assumed to be the r. The self energy of this spherical shell is kq square upon 2r plus the interaction energy between the q node and the capital Q, that is kq q node upon r. You understand or not? Right. Now in place of this q node, this is the q1. So you have to write the self energy of this q1, also the interaction energy between q1 and q2, which is kq1 q2, and the separation between them is r2. All right, copy this. So let's discuss one more concept. Suppose if it is the q and you are bringing the charge q from the infinity like this, right? If it is distance x, the electric force is this and this is the external force. So if you are bringing this charge, right, slowly, the external force and the electric force must be equal in magnitude in opposite direction. So what the work done, external work done is you have to do from infinity to point P is nothing but, suppose this distance is r, right, kq upon r. Is it clear or not? Is it clear? But the work, what is the work done by electric force? But the work done by the electric field is nothing but minus of the work done by the external agent is equal to K minus Kq₂ upon R. Is it clear or not? If this point charge is bringing from infinity to this point Q at separation, this point P at separation R, work done by the external agent is Kq₂ upon R, and the work done by the field will be just opposite. Is it clear or not? Also, listen one thing. If this is the capital Q charge, right, and this is the initial position of the small q charge, right, this distance is R1, and you have to bring this charge from position A to position B, and this separation is assumed to be R2, right? So you have to work, external work you have to do. What? In moving the point charge from A to B is equal to the change in potential energy, U final minus U initial. Is it clear? Here the U final is what? Kq₂ upon R2 minus Kq₂ upon R1 is the initial potential energy. This is the external work done. And if you want to find the work done by the field, field means the gravitational field in that case, here the electrostatic field. The work done by field is just opposite to the external work, and therefore it is equal to minus UF minus UI. Although the UF minus UI may be the different, here only the 2-point charge I have taken. So you can write minus the work done by field is equal to work done by external agent, right? If you adjust this minus sign is equal to change in potential energy. So this is not only for this case, rather for any type of the conservative force, right? This is for, since electrostatic force is what? Electrostatic force is conservative. Force is conservative. That is why, right, the minus work done by field is equal to work done by external energy is equal to change in potential energy, right? So you have to apply, sometime you need to find the external work. So what will you do? You will find the initial potential energy, final potential energy of the system of the charge, and you can find the external work required to change the configuration of the system of charge particle. And if they ask the work done by the field, just take the negative sign, you will able to find the work done by the field. Is it clear? Copy this first. So listen one thing, from this expression we can also write the conservation of mechanical energy. If you take these two terms, that is the minus of the work done by field is equal to change in potential energy. What is the work done by field? The work done by field is nothing but total, what is the work energy theorem? If external force is not present, right? What should I write? If you, this is the thing, if only electrostatic force is present, electrostatic force is present, no external force and no F external. F external is you assume to be 0. So what is the work energy theorem? The work WET is nothing but total work is equal to change in kinetic energy, and the total work is done by only the work done by field. If only the electrostatic force is present, right, in moving the two, right, in changing the configuration, only the work is done by the field. And what is the work done by field? The work done by field is nothing but minus U final minus U initial is equal to K final minus K initial, right? Minus U final plus U initial is equal to K final minus K initial. So here the Ki plus Ui is equal to Kf plus Uf. That is the sum of the initial kinetic and potential energy remains conserved is equal to sum of the final kinetic energy and the potential energy if external force is not present, right? That is total mechanical energy, total mechanical energy remains conserved, if no external force is present, no external force is present. Fine. Copy this. So read this question. In this question, consider the configuration of system of the charge particle, 4 charge, each of value plus q, right? And this is the placed at corner plus q, and this is plus q. The separation is, now it is converted into, right? This is the first figure. Now it is converted slowly, right, into the second figure. This is the second figure. This is the plus q, and plus q, and this is the plus q. Is it clear or not, you tell? So here the initial potential energy you have to find, the final potential energy you have to find, and then subtract them and you will get the external agent work. So the initial potential energy, in initial potential energy there will be the 6 terms: u1, u1, right, u2, u3 and u4. You understand or not, you tell? Right, this is the u1, u2 and u3. Also this is the u5 and the u6 we have found, right? So these 4 terms are similar. So 4 into k qq upon a, plus these 2 terms will be equal 2 into kqq upon a root 2. So the kq square upon a, 4 plus 2 upon root 2 is the initial potential energy. All right. And now in this case, the final potential energy you have to write. The radius is assumed to be the a. Fine. So again you have to write the potential energy of this system. The 4 charges are there. The total 6 terms will be there, right? u1, u2, u3 and u4. Is it clear? So these potential energy terms are equal. So 4 times kqq upon, the separation between them is what? You tell. If the radius is assumed to be the a, this is a, this is a, this distance is a root 2, right? So a root 2 is the distance. Is it clear? Plus 2. The 2 terms will be u5 and u6, and the separation between them is 2a. You understand or not? So what is the total potential energy? Kq square upon a, if you take common, 4 upon root 2 plus 1, right? This is kq square upon a, 2 root 2 plus 1 is the final potential energy. This is the initial potential energy. This is kq square upon a, 4 plus root 2. This is the initial. So what is the external work done? The external work done is nothing but change in potential energy. This is the final potential energy, kq square upon a, 2 root 2 plus 1, right, minus initial potential energy, kq square upon a, right, 4 plus a root 2. So this is kq square upon a, 2 root 2 plus 1 minus 4 minus a root 2. Kq square upon a, right? How will you get? This is the root 2 minus 3 is equal to external work, right? Is there any? Okay, so this is the answer. Option is not given, right? Copy this. Read this question. The 3 charges plus q, minus q and the minus 2q plus 2q, right? This is the plus q, this is the minus q and this is the plus 2q, are placed on isosceles, right triangle. So if this is a, this is a, this is a root 2. So the total potential energy you have to write. Assume this is, these are the, this is the u1, u2 and the u3 is the interaction potential energy between the 2 point charges. So u1 plus u2 plus u3, you are going to write u1 is kq2q upon a, between this kq q upon a, between this kq q upon a root 2, right? So kq square upon a, kq square upon a, if you take common, 2 minus 1 minus 2 upon root 2, Is it clear or not? So it will be equal to kq square upon a. It is 1 minus root 2. Is it clear or not? 1 minus root 2. So the total potential energy is negative this time, because kq square upon a, and this is what? Root 2 minus 1. This is the total potential energy. Okay. So read this question. You are given an arrangement of 3-point charges q, 2q, right, and minus xq upon 3, separated by equal finite distance. Suppose the distance is a and the distance is a. Is it clear or not? Separated by equal finite distance. Oh, they are not like this. Then equal finite distances like this, right? This is minus xq upon 3. That is, they are separated by the distance a. That is, they are on the corner of the equilateral triangle. If the total potential energy of the system is 0, right, then you have to find the value of this capital X. So how to write the potential energy? U1, U2, right, and U3, right. So U1 is nothing but K, Q, Q1, Q2 upon A, K, Q1, right, Q2 upon A, plus K, Q1, Q2 upon A. And the total potential energy of the system is what? 0. So therefore the X value you have to find. The kq square upon a, if you take common, here minus x by 3, here kq square upon a common, so minus 2x upon 3 if you simplify, 2 upon, and this is the plus 2. It is equal to 0. So therefore minus x by 3 minus 2x by 3 plus 2, right. So if you take common x by 3 plus 2x by 3 is equal to 2. So the x, if you simplify, x is equal to 2. That's it. So the value of the x is what? 2, right. Copy this. So read this question. In this question, a charge minus q and a plus q. This is the plus q, suppose, which is fixed, and this is the minus q, are kept between at the point A and the point B. Now keeping the charge q, it is fixed, and the charge minus q is moved to another point C, such that this is the C. It moved, this minus q is taking to the point minus q right over there, right. So that now this is the plus q which is fixed, and now it become point C and the minus q is over here, right, such that this is A, this is the B, this is C, right, like this. Are you getting or not? So you have to find the work done in moving the charge from here to here, right. So the work done is nothing but the change in potential energy. So initial potential energy, if this is the equilateral triangle, the distance A, assumed to be the distance A everywhere, right. So ui is equal to what? K q minus q upon A. And what is the final potential energy when charge q is placed over here? It is K q minus q upon A. So I think initial and final potential energy are same. So what is the external work? Say uf minus ui, both are equal. So the external work done in moving the charge from point B to C is what? 0. So the D option is the correct option. This is the one thing, right. Listen one thing. If some work is done, and this is the example, I am giving you one more concept. Since the electrostatic force is the conservative force, if this is the plus q, it is fixed, and this is the minus q. So if it taken to this point by the path 1 and path 2 or the path 3, right, like this. So the work done in moving from B to C, external work done from moving B to C, whether you choose the path 1, whether you choose the path 2, whether you choose the path 3, all are same. Is it clear? From here to here, the work will be the same. because the electrostatic force is conservative force, and the property of the conservative force is that the work done depends upon the initial and the final position, does not depends upon the path chosen, right? So this is the one concept and this is the solution, right? Copy this because it is very necessary to cope up with them, otherwise less marks are obtained, then it is not good, right? Because they will take the test what they are teaching, right? And ray optic itself, yes, yes, that is okay. But April, the next month, after few days, the April will come, and the ray optics is a very big chapter, and at least 20-25 days in the coaching also. 3 week it will take at least. I don't know how much time they will take, but at least 3 weeks it will be finished. And ray optics is a very important topic, right? So if I will try to finish this, the important topic I will cover in the electrostatics, and the remaining topic we can continue to later. I will suggest you to start with the coaching institute because the marks we have to bring, right? And the ray optics is not very easy, right? It looks easy but not very easy, and the JEE mains and JEE advanced, for both exam it is very important, right? If you want to continuity in evening, not continuously, right, in the evening class we can start with the ray optics, right? You can check, yes, you can check and let us, because nowadays the class 11th, right, is not there, the dropper are also not there, so I'm also free, so few days, right? That is why I'm saying I'm also free for few days, at least one month and 1.5 months, so I can take your class in the evening also. After few months, right, after 1 or 2 months, I have also the less time. So if you are getting the time in next 1 month, at least next 1.5 month, 1.5 month, so in evening you can also continue regularly, right? I will suggest after that, when the syllabus is completed, then you will feel relaxed, and I am also feel relaxed because the ray optics is itself a very big topic chapter, right?